everyone. Welcome to our panel session here on low power design. It's entitled What's Hot and What's Not in Low Power Design. So we have a distinguished panel of speakers here today who will talk about various aspects of low power design and where we are today. But before we do that, I just want to tell you just a bit about SiTU, as we are the sponsoring organization here. SiTU is an R&D joint venture, and we develop interoperability solutions for IC design tools. We have several different initiatives underway currently. This includes open access, which many of you are probably familiar with, industry standard database, compact models for SPICE, which you're probably familiar with as well as OpenStandards, which is what the organization that I lead, where we develop new standards and new technologies for IC design. We have several different areas of focus. Low power design is one of them. We also have silicon photonics, chip package co-design, process design kits, and design for manufacturability. We have quite a large number of members. You can see the whole list here. I won't go through that, but I just wanted to give you a bit of an overview of who we are. So, to start off the panel, I want to give a little perspective. And I'm entitled this, What Was Hot? So, over time, and I'm not going all the way back in IC design history, but in the mid-'80s, one of the big application areas for IC design was super mini computers. The circuitry was running at 5 volts, typically NMOS at the time, and we ran into power issues. The technology that was brought to bear at that time to deal with those power issues was a switch from NMOS to CMOS. And that was a process solution. And as we go forward in time, we see that the applications that we targeted generally as an industry changed and became more power sensitive, such as laptops. But we also brought other solutions to bear to help us reduce power consumption. In this case, in the late 80s, early 90s, we began to see gate-level power analysis tools from the design automation community. Following that, around 1995-96, we saw RTL power analysis. Going forward in time, the applications became even more power sensitive, such as cell phones. We also saw a drop in the supply voltage. That drop was actually not driven by low power design. It was driven by reliability issues, but it helped us in low power design. And that reduction in power supply levels continued to drop as we went forward. And we brought other solutions to bear, gate-level power optimization. Power gating was deployed to deal with leakage issues that came about because of the reduction in supply voltages and threshold voltages, and so forth and so on. The voltages continued to drop because that was a big lever. We continue to go forward, and in the mid-2000s, we saw the development of power intent specifications for CPF and UPF. And the applications became even more power sensitive. Here we have smartphones that now they're not just phones, they're doing all sorts of things. We're quite familiar with that now. But the more functionality that was crammed in, the more important it was to reduce power consumption. Voltages dropped even more. Now the process folks jumped in to help us. We saw the development of high-K gate dielectrics and then FinFETs to help reduce leakage. Voltages continue to drop. So now we see the advent of ultra-low voltages. And furthermore, the use of 2.5D and 3D designs to reduce parasitics, bring devices closer together so it doesn't take as much power to communicate, and also system-level power models. So this isn't meant to be a complete list of the various technologies that have been developed. Rather, the idea here is to show that over time, we have seen different technologies that at the time were hot, but later on we look back and we see, okay, now they're commonplace. We all depend on that, and we need more. So what I've asked these panelists to talk about is what's out here, what's hot now, what might come further on. Let's give us a view from the leading edge of what's happening and what these leading designers expect to happen. So, I mentioned that we have a distinguished panel here. We have Nagu Dhanwada from IBM, Erin from AMD, John Redmond from Broadcom, and Frank Schurmeister from Cadence. And I'll ask Nagu to start out. I'm going to get his bio off my phone. I'm not looking to make a call here. So Nagu Dhanwada is the low-power tools and methodology architect at IBM, who leads a global team responsible for developing and delivering low-power and thermal tools and methodologies in IBM Systems Group. Nagu holds a PhD from the University of Cincinnati. He has worked and led various projects in early physical design planning, electronic system-level design, and architecture modeling. Nagu has been the Science Area Coordinating Committee member of the Semiconductor Research Corporation. Nagu actively works with universities and has mentored several projects in the areas of system on a chip, low power analysis and design, and also co-advises PhD students. Nagu has served on NSF panels. He works with several industry standardization efforts and is the chair of the SiTU Low Power Correlations Technical Steering Group. He also chairs the IEEE 2416 Low Power Modeling Standards Working Group. He holds several patents and publications in the areas of system-level design, power analysis and optimization, early physical design, and analog design optimization. Nagu?
There are actually three things which you're noticing from my point of view on what's hot. The first thing is, of course, local self-heating, right? No pun intended. Where, with the scaling, right, even from 22 to 14, there's actually a lot of local self-heating effects, coming in, device-level self-heating, and being able to assess and mitigate these kind of self-heating effects will be a key aspect, right? More than anything else. So that will be a problem which we notice, and which tools, methodologies, everything would need to address at some point of time. Yeah. The second one, as Jerry mentioned, we'll be trying to optimize for power. So total system power optimization means system level power, both from a modeling standpoint and optimization standpoint, right? The third piece is also standards, right? So that's kind of been, it is important. We heard even in the keynote today, for really this total system optimization with IP coming from different places, standards play a very important role, right? So I'll actually touch on each of these three things briefly to make my position statement. Yep. So local self-heating, right? So traditionally supplying and really the thermal dissipation has mainly been like a chip and chip design module kind of an issue, right? But with scaling, we are finding that device level self-heating is actually becoming very, very, very significant. As much as 10 to 20 degrees centigrade, you see local micro hotspots, not just in high voltage stress modes, but really in traditional operation also. And this is because you have multi-fingered, multi-fin devices, which actually get very hot, and you kind of see 20, even 20, 25, 30, or even more centigrade at the local device level. So it is a concern, and actually it's not just traditional approaches of just, hey, at the very last minute you're trying to simulate, your circuit designer is trying to simulate with the circuit simulator and trying to get the self-heating impact. That really is not enough. I mean, that's still needed for very accurate sign-off, but if you can manage this early on, right while the macro is being constructed, being able to assess these kind of impacts early on is a significant thing. And I think we had some posters also which talk about what we try to do here, but that is something I think which would need some attention, and which definitely is something that needs to be addressed in the design methodology. Yeah. So system level power, right? I mean, this is, we've heard this, I think Frank was telling that, yeah, we keep hearing this every 5 years. I mean, this is kind of, has been there for a long period of time. I think it will be there, it will continue to exist, and there are different solutions at different points of time. One thing is, yes, what we're trying to do here, we want to enable trade-offs at a higher level. Right now, call this at a component level or a system level at different levels of abstraction, but that's really something which needs to be addressed. And the key part of it is really getting the system and the components that make up the system, the power model for all of these in place. Right? That's actually a very key aspect. And these models should really be interoperable, right? I mean, if someone gives me a model and I have a system with an IP from vendor A, vendor B, and I have my own IP, I should still be able to do some trade-offs at the system level with these disparate set of IP sources, right? So that's the whole idea. If you have such interoperable models which span across levels of abstraction, that will actually give you early views into power characteristics of the complete system, right? The next aspect is even more important. Again, you heard with 14 nanometer and later, dynamic power is taking a lot more importance. There's maybe 25% of leakage, 60-70% of the chip power is coming from dynamic power. So that kind of brings the whole application impact on power. You run, what software do you run? How do you actually get the actual vectors when you're doing these kind of analyses? That's another challenge which needs to be addressed, right? I'm sure. So, and then of course, getting to understand the thermal impact of system power optimization, right? So you have, you're trying to do some very fancy voltage and frequency scaling, or you're trying to do some throttling, and you have maybe a lot of architectural decisions you're trying to do to optimize power. But what's that impact on a thermal sense? And this kind of goes back to the models, right? I mean, are your models parameterized enough? Can you really do this kind of exploration with reasonable degrees of accuracy when you are at this level of abstraction, right? So that's really some of the highlights in the system level power area, I think, which we need to pay attention to, and I'm sure a lot of people are doing. But that's in my view what goes into the system level power part of what's taught, right? Last but not the least, right? I mean, standards are important, especially when we are talking of systems composed of disparate sets of IP, right? Three things, in fact, I'm showing a picture of some of the IEEE efforts in this whole standardization space. There are actually the 1801 standard, people are familiar with what it's about. There is a 2415 and 2416 standards also, which try to address the software side of things, is what 2415 tries to address. The 2416 actually tries to address, formalizing the notion of having process voltage and temperature independent power models, right, which is very key for some of the system level explorations, considering thermal impacts, which I just talked about in the last slide, right? So, again, there are standards work, and standards again become very important in this scenario to be able to further the next level of optimization, system level power optimizations and such. Yeah, that's.
Thank you, Nagu. Next, we'll hear from Erin from AMD. Erin is an AMD fellow. Erin has 18 years of industry experience in individual contributor and management roles, with a wide background including architecture, design methodology, circuit design, and silicon characterization and debug. Erin's current role is leading a centralized power architect team that owns power frequency modeling, power feature development, and general design for power activities. Erin.
Thanks, Jerry. Yeah, so today, kind of in a similar tone, I'll talk about kind of in the recent past, so this is kind of what's not hot to me. This is some of the big advancements that we've seen from a number of companies. So I kind of wanted to walk through this list of things that, if your companies haven't come up with solutions like this, you should be, because this was leading edge 3-4 years ago, but it's quickly becoming the trailing edge, right? So as I walk through this, the big one to me has been all the adaptive techniques that we've done. And the first is for droop mitigation, right? AC droop in your power delivery can, loses a lot of voltage, and at the end that means you throw away a lot of frequency and power by adding additional voltage guard bands in the system. I presented our solution from AMD at ISSCC in 2014. I came back in 2015. I think there were 5 different presentations of companies doing something similar, right? Very, very hot the last couple of years, but certainly on a trailing edge. We haven't been there. The next is voltage regulator tolerance guard band reduction, and again, several people have published in this area, including AMD. I presented again this year, 2016 ISSCC, which is really a method for removing aging guard band, so that we can track the aging of the devices at boot time. Also remove the voltage regular tolerance, and then also track from a binning methodology through the manufacturing flow the differences in power delivery quality between an ATE from a sort insertion to a packaged ATE insertion to a final system level test in an end system. And then to not add guard band for any of those stages, but instead to compensate based on adaptive techniques. A third one that we've seen from a number of companies as well, I like to think ours is the best, but which is our adaptive voltage frequency scaling. So this is really understanding on a per part basis what the voltage versus frequency curve is, and understanding not only per part, but how that changes across temperature. And so that you're always picking the exact voltage you need and never any more, further reducing guard bands. AVFS also naturally gives you temperature inversion guard band removal, since it's tracking the F versus V as a function of temperature. And lastly, Vmax relaxation. One of the biggest, in a lot of applications, mobile applications, race to idles when you win. And you can race to idle and actually save power, deliver better better end-user experience by actually running higher power and frequency for a very short amount of time and shutting down the rest of the system subcomponents. Ultimately, Vmax was limiting our ability to boost in many cases, as it is for a number of you. And with our ability to track reliability over time in the part, we can determine how much we can safely boost within our reliability limits to improve that race to idle. So again, all of these have been published AMD solutions, and if you go look at the last 3 years in all of those journals, you'll see that there's just a myriad of these solutions coming from different companies. So that's what was hot in the last couple 3 years, and in our case, we put these all together. It's greater than 50% performance per watt, right? That's a lot, right? But it's mined out, right? It's not hot anymore. Incremental improvements maybe, make it easier to get it productized maybe, but no big, there's no big, I'm going to get another 20% here, right? So to me, what's hot in the near future? So integrated voltage regulators. So, and this again has been something that on a lot of IPs have been published. This isn't anything new. In our case, in my view, in a lot of cases, their benefit has been relatively modest. But there's several things happening in the industry that are going to make this more important. A good example of that is the cache coherent interconnect for accelerators, or the CCIX. So this was announced just 2 weeks ago. It's a joint standard being developed between ARM, AMD, IBM, Mellanox, and Xilinx. I know I'm forgetting a couple. Anyway, but the point here is part of this interconnect allows us to put all these IPs in the same package with a very local interconnect technology. Well, what does that mean? Well, now I've gone from a heterogeneous system that may have 8 clock domains to one that could potentially have 40, right? And every clock domain is going to want the optimal voltage to run its workload and to power slosh between them, right? As the workload progresses through the various units. Well, we're not going to put 40 regulators down the motherboard, right? So to get power efficiency as we continue to integrate IP, internal voltage regulation on die is going to become more and more and more important. Next, platform level power management, and this goes to the platform level power modeling. You can't go do good power management at the platform level if you can't model and understand it, right? And really, to me, this is, again, I didn't even put it on my list because that's so old news. It's not even the past 2 or 3 years. It's all the power sloshing that's done in your smartphones and PCs today, right? Based on what the workload is doing, you either have hardware or firmware or some combination of the two that allocates power budgets and shifts the DVFS point for all the IPs in the system, so in the SoC. Well, that's old news. Now we got to do the same thing at the platform level, right? We got to figure out how to allocate power to whether it's the display, whether it's the hard drive, whether it's changing fan policies. You know, those are the kind of things that are the next level in terms of power management itself. I see that's where I think the industry is going to go. Better electrical design, current thermal design, current mitigation techniques. And this again goes to the process scaling that Jerry points out, right? As VTs continue to drop, what's happening? In my same thermal budget, my thermally constrained power budget, right? My voltage is dropping, which means my current is increasing, right? And it's starting to become very challenging to get enough power out of the regulators that we have on our boards without violating EDC or TDC. EDC being the thermal saturation of the inductor. And you know, the good enough techniques that we may have had in the past to shunt that are not going to be good enough anymore when you look out to like 7 nanometer. We're going to have to get very either architectural or circuit techniques to solve that problem. Another one is physical design. So the wires, as we look forward to 7 nanometer and beyond, the wires are getting really slow and high power in the lower layers, and you get significantly less good fast metal per logic gate. And so almost nobody does very full custom or data path manual design anymore. My question is, are the tools going to keep up? I don't know. And then that's just an open question. It certainly concerns me as we started looking, when you start looking at ahead to 7 nanometer and beyond. It's not clear to me they will. And lastly, data movement power, and this also goes with the technology scaling. Ultimately, you've got a bunch of I/O, and you're going to pack as much logic as you can into a high-performance chip. As you do so, your compute units get smaller and smaller and smaller, and fundamentally they get further and further and further away from the source of their data, right? So a combination of circuit and also architectural techniques, whether it's data compression, whatever, are going to have to be implemented more and more aggressively. Some of these things are being done, but it's becoming more and more important particularly as some of the analog structures don't scale like PHYs. So that's sort of what's hot on the horizon, and thank you.
Thank you, Erin. That was a particularly interesting look forward. Appreciate that. Next up is John Redmond from Broadcom. John Redmond is a low-power technologist at Broadcom, focusing on low-power technology development. He has been instrumental in the development of power estimation and reduction methodologies, power management, power intent flows, and adaptive voltage scaling. John previously worked at Nokia and Connexent on low-power wireless SoCs. John received an MS in computer engineering from Iowa State University. John?
Thanks, Jerry. So I don't have any slides today, so I'm just going to talk about what's hot and what's not. So I started my career out in cellular, where power was the primary constraint. And a couple years ago, I moved over into set-top boxes. Set-top boxes, power is becoming more and more higher priority in the power world. That's due to regulations such as Energy Star and voluntary agreement, and also set-top box is now consumer expectations for the form factor is smaller and smaller and smaller. The same evolution that went in cell phones also. The cell phones are out bigger and thin is in, and we just went smaller and smaller and smaller. So we had to, boost compute and stay in the same thermal envelope as we get smaller and smaller and smaller. One thing, before I was into low power, I started my career in silicon implementation, and Jerry kind of showed a little bit of that earlier. But back then, timing, so silicon implementation, synthesis, SDA. Back then, that was the challenge for a block: is how do you close the timing? You'd spend a lot of time, changing RTL, over constraining, tooling knobs in the synthesis tool, etc. And every block had a different timing recipe. Maybe you group paths, or maybe you ungroup some hierarchy, or every block had a little recipe for timing. So fast forward to now, the industry has solved that problem, the EDA vendors, the library providers, etc. I mean, most blocks today, timing closure is not a challenge because you swap in lower VT cells and timing's met. So we're not putting in as much effort. And it's kind of very similar today as what we're developing for our blocks is a power recipe. So instead of spending that that effort into timing, now we're spending it into power. How can we reduce power in our blocks? And each block has a different recipe, maybe a different clock gating style. Maybe some blocks do well with sequential clock gating. Maybe some do well with hierarchical clock gating or multi-stage clock gating. So, we're really focusing our efforts now on power instead of timing. And I think that's in one discipline of silicon implementation, but I also see that, in architecture, verification, design, RTL development, etc., where, we're really focused now more on power. The recipe, for the blocks also includes, leakage mitigation. So the idle mode leakage problem is generally a solved problem. UPF is there. The industry came together, standards groups, design companies all came together, got UPF off, and the whole power gating is pretty much a solved problem now. So what's our new problems? For sure, active power is now the challenge. We solved the off-state power, now it's active power. So both active leakage and dynamic power. So I just kind of wanted to give a grade on how we as an industry are doing in power estimation, power analysis, and power reduction. So I'll start at the lowest level of abstraction, which is gates. And I think, at the gate levels, estimation's good. We have really powerful tools for analysis. And, we have a handful of push-button reduction techniques. So, I give us, as an industry, an A. At the next level of abstraction is RTL. There's opportunities in RTL with usability. We have a tool set. We have a pretty good tool set, but, there's still some usability problems. So I'm giving us a B there. But at the system level, that's where I think there's a huge gap. I know Erin spoke that it's a solved problem, and I think it is solved in a proprietary fashion. I think each company has their own way of dealing with system level power. But I think as an industry, as we share IP, as we get third-party IP in, how do we model that power? That's a problem. And at a company like Broadcom, we get third-party IP from outside the company and also internal. We have a lot of internal IP providers across the company, and we don't have a great way of sharing that system level power. So the grade for that at the system level I give is a D. I think as an industry we're failing. I think there's opportunity. I think it's something that needs to be solved. And it's Erin spoke about all the different techniques and great techniques, and oftentimes what we do today is we know they're going to save power, so we throw them in. But if we had that system level power modeling and we could do what ifs, we could try, do we need 3 DBFS points or do we need 11? That type of question, that kind of what if analysis and trade-offs, it's somewhat difficult to do today. Even the system level power modeling we do today with an Excel spreadsheet, it's hard to get a good stimulus in, right? Oftentimes we're just modeling duty cycles and active power and idle power. So the modeling, the proprietary modeling we have today, some companies are better than others, granted, but the problem is the exchange of IP models, the richness of what we can do with what if. Those are seriously lacking problems. So I think that's the grand challenge today, as Jerry put it, that we have every generation or every couple of years there's a different challenge, and I think that's the challenge we're at today. And I'm looking forward to the industry again getting together, just like they did with UPF. You get the standards committees, the design companies, the EDA companies all come together and solve the problem. Thank you.
Thanks, John. Just remind me not to take any of your classes. You're too hard of a grader. Next up is Frank Schurmeister from Cadence. Frank Schurmeister is Senior Group Director, Product Management, System Development, System and Verification Group at Cadence. He is responsible for product management of the Cadence System Development Suite, accelerating system integration, validation, and bring-up, focused on virtual prototyping, acceleration and emulation, FPGA-based prototyping, and software-driven verification. Frank holds an MSEE from the Technical University of Berlin.
Thank you very much. So, power, interesting challenge. Just to define a little bit how we at Cadence look at a SoC, a modern SoC, you will have lots of components here. You have things like an ARM subsystem, you have lots of IP components, often reused. That's an interesting challenge as described earlier. Interconnect, that's where all the data movement goes, which was described earlier. We have in there, besides these IP cores, we have lots of software cores. So we have multiple cores here. There are more cores hidden within the actual components, and you have lots of software in here, right? From bare metal software, which may define like graphics environment or DSP-ish algorithms here, to the application software, which seems to be wearing down my phone all the time, to the communication software, which enables the communication across channels. So these complex chips are very, very complex, lots of software in the system, and when you develop them, you want to make sure that you do all the analysis, all the optimization as early as possible, because if you look into a design flow, about halfway through, you have to fix a lot of items, right? So if I haven't figured out by the time my RTL gets stable, whether my hardware software actually works, and what my power consumption is, doing it late here is in the noise. So the earlier you make all your adjustments in a design flow across the whole system, from IP through subsystem, SoC, the hardware itself, and then the software stack on top of it, the more impact you will have on your power consumption. So a couple of things people do today, just to look into the state of the art. If you look into metric-driven, power metric-driven verification, what people are doing today is they will look at shut-off of and take the power intent as it is standardized with CPF, UPF, and will drive it into incisive things like RTL simulation and into emulation, and they will essentially figure out how to verify the different power modes, the different scenarios, and then we're dealing with fun effects here, where you're now so accurate in modeling this power shutoff that you end up having effects like the software guy complaining the hardware not taking their inputs by programming registers. Well, when you verify, it turns out the item they want to actually write into has been just shut off, and these mechanisms actually are modeling this fairly accurately so that you can get these hardware-software effects under control. The other item is being able to look into power over time, which gives you the energy, and basically find the peak areas here. That's where you do dynamic power analysis, where you really take the toggle counts from higher level engines like emulation and feed them into RTL estimation. I found the grading quite interesting, which John gave, because it's interesting if you then look into the different implementation tools, right? So at the level of a Walters and looking into gate level, you indeed get very good estimates of that individual piece. You then abstract it into the higher level flows, even up to virtual platforms, where you have essentially TLM-based, transaction level based simulation. Where we are certainly not doing great stuff yet is at the system level, where you have transaction level based simulation, being able to consider all the changes, right? So with RTL power estimation, I think you gave us like a B- or C, somewhere there. This is getting better as the engines are correlating with the implementation more closely, but we don't have the full accuracy in here yet. In the ideal flow, this vertical integration would actually work really well, that I make a change up here at the system level, and I find out immediately with fast synthesis, with predictions, with an estimation, what the effect will be as I go down into implementation, and you annotate that back into the front end. Right, so if I look, this is a graph I literally keep on the system level. That's why I was joking in the prep here. Old slides, kind of like the Bell pans are becoming new again within specific cycles. I used this slide first back in 2005, so literally 10, 11, 12 years ago, by really looking into the different components of a chip, from software through analog, through the memory and the data flow hardware, and basically looking into how, at which level you have the biggest impact with your optimizations, right? Of course, at the time I was with a company which did high-level prediction, high-level synthesis for low power. So, but the principle is still true. The earlier you actually figure out how to optimize these, the more impact you'll have later on in the implementation. So being able to deal with deep cycles here, long software-driven analyses is important. Better hardware representation, so being able to represent the gate level, the RT level for the higher level is becoming more and more important. Hardware-assisted techniques are really no longer optimal, optional. You can really not afford to just do simulation, or even later at the implementation level, your analyses. You need to get this to higher levels of abstractions and longer cycles. The annotation across abstraction levels, you mentioned that, and I basically referred back to our grading at the different levels. That's becoming more and more important. And then separation of concerns. I see more and more people, colleagues over here of Synopsys, for example, did interesting presentations on how you put into the software, like an Android boot, you put power events into the software, so you separate your concerns of software and hardware pretty neatly here. And there's a lot of shift-left work going on in low power, where you're trying to model the operating system and so forth and get the power impact analyzed from there. So as I'm always joking, this will be enough things to do until I get my daughter through school, which is at least another 10 years. So there's enough work to be done and dealt with to keep me safe there, to get her through school.
Thank you, Frank. It'll be interesting to see, looking ahead, how many more years you continue to use that slide. So at this point, we've got some time for some questions to the panel. I'll start this off and pose a question to each of you. And it relates to system level power modeling. One of my favorite quotes about system level stuff is, when I don't know who said this, but when asked, what is a system level, the reply is, oh, that's the level above which I'm working. So I'm curious, what does system level mean to each of you? What does a system level power model look like? We'll start right to left. Nagu?
For us, we're mainly a microprocessor company, right? From a microprocessor point of view, yes, I mean yes, I mean two system can be your rack or anything else, right? But typically when we're hardware design cycles, you still constrain yourself to really the boundaries of what we call as a chip, right? I mean chip meaning your processors, your fabric, your nest, what we call it, everything else, right? And I mean that's really where the boundary of definition of a maybe call it a chip level, but that's really the top level where you operate it, right? Now obviously there is another level where, yeah, I mean you'll have like the platform level management, which Erin was mentioning, right? Where there is, within your bigger system, there is software which does, data center power management. There are actually layers of software there. But personally, for me, hardware design perspective and everything, it kind of, the chip is your processors, your fabric, your everything else that really goes into your chip, right? That's from my perspective, right? So, Erin?
Yeah, that's why I kind of intentionally use the term platform versus system, right? So from my perspective, you kind of have the physical layer stuff, right? The physical box, right? That's what I'd call the platform, the level to which we're, a lot of the modeling we're doing kind of stops. But there's certainly a huge software implication. So whether it's your drivers being optimized, et cetera, and all that has to be modeled somewhere too. I don't know if those things ever want to be really the same model and be a true system model, or whether you have a platform model and a software model. But that's why I kind of intentionally make that distinction and say platform, because the system really does include the software, which I think it's to do higher level modeling is a more complicated beast, right?
Yeah, that's where I think the boundary kind of goes between, like anything we do with software is just like another activity or another workload for what we are doing, right? So it's kind of treated, yes, I mean there are modes and everything, but as long as you can get that activity, what you call as activity from software, that really kind of dictates.
Yeah, to be clear, you have to model what the basic application is doing. Is a high power, low power application. I meant in terms of having a model such that you can optimize, your software, whether it's OS interactions or whatever, and still have the full physical view of the platform.
Correct.
That's where I think.
Correct, yeah. So coming from Broadcom, this is an easy one because we like to integrate everything. So the system in a cell phone was everything downstream of the battery, and then something that plugs into the wall is everything downstream of what gets plugged in. And the reason is because next year, whatever multiple chips, we'll just keep integrating together. Like in cell phone, we integrated radio, PMU, and baseband all together. So we're driven to integrate. So Erin's definition, I guess it would be the platform. So that's how I define system. And I think the other thing is no matter how you define it, it's effectively how we model it, it'll be the same. So whether it's an IP on our SoC or if it's an IP off our SoC, how we model it's the same.
So I think from an EDA perspective, the customers I am interacting most with would consider the system the chip plus its environment, including all the software, right? So you two are customers of us. And if I look in the diagrams I see there, to pick one from Alex Starr in emulation, it's essentially the full chip, but then integrating all the SATA components, integrating all the outbound components. So the system becomes a chip plus the software plus its environment. And the level of optimization you then want to do is really defined by scenarios, I would say. With scenarios I mean things like defining what happens if I decode a video for transmission and simultaneously present it at a video output. So all the effects you described earlier, Erin, the notion of like having heat issues locally. Nagu also was talking about the issue of locally having heat issues because of too much activity. Those you can then look into once you have the scenario defined, understanding which of the components are switching on which peripherals, and that gives you a system power view, if you will. And that includes then different perspectives. The software perspective, basically saying, hey, if I move my data somewhere else, I have less transactions, and that because I keep things more in the cache, that is helpful for power as well. Then you have the hardware perspective of looking at all the transactions going on chip and what that causes in the implementation for the dynamic power consumption. And you have kind of the architect's perspective who's trying to bring it all together between hardware and software, figuring out, oh, this task, should I really move it somewhere else or even consider a dedicated hardware piece because it's causing me too much power consumption if I do it all in software.
Okay, thank you. Those were interesting perspectives on a somewhat provocative question. Let me open it up. Yes.
what you've got, is that the reason, or do you also have the self-heating problems in your applications?
So from my perspective, oxides, I mean, we have it, but it's not a problem. Nagu was mentioning 30C deltas. We're not seeing that. So we have it, but it's not a problem.
So we have it, and we guard band for it when doing our power calculations and our firmware loops, right? So we know there's a hot spot, right? And for our reliability limit, we know we have to cap it based on what that hot spot could be versus what we're measuring at our various thermal sensors, right? Because we do know there's a gradient, and that 30C number is not that different than what we see, maybe a little less, but than what we see, maybe a little less. But the point is we guard band for it, and if the question is, do you see value in fine-grained thermal sensing? The answer is yes. If we can make a reliable one, that would be very useful, because we wouldn't, not only would we not have to guard band for reliability purposes, we know what our true hotspot is, but we also could remove guard bands for our power limits inside of our power management firmware that we're reading with thermal sensors.
It's more of a safety. Any other frequency at which we're talking about, so right? In John's case, relatively low frequency applications, and here we have thousands of really high frequency applications. Right? So,
Power is a better word.
Yeah.
Well, but that gradient's important. That gradient's important, right? If you're running, processor at 4 gigahertz, right, and one unit is very active, and let's say you're not running any floating point code, right, and your therm sensors in your floating point, it's going to be a lot cooler than in the middle of your load store unit, right? When you're cranking away with NPX code at 4 gigahertz. Right? So I think the frequency in the application is.
Is this for my hourly rate? How much is this damn costing?
Yes. Oh, sorry.
My question to the user companies are, do you see value of standardization in the system level area? The work has started, but do you think it is stable enough to standardize some of the areas, and is that something you would use in your flow and your tools?
Yeah, I mean, we would. I think we. We're always concerned with proprietary solutions.
Right.
We've got a handful of super users on our own tools, but absolutely we can standardize.
Okay.
But I haven't seen, and maybe I just need to get up to speed, is a good going all the way back to the process, underlying process technology, and all the way through this sort of what I call the platform level.
Right.
I haven't. There's nothing. That's what we need. And until we can get something that does that, we'll continue to make our own tools that do it. Right?
Okay.
Yeah, I agree with that. We'll definitely use them once one piece of the puzzle is standard, the second piece of the puzzle is the tools. So Aparna, I hope you can get some tools. So, but yeah, I mean, we'll definitely use them, and I think if it makes, our power, energy, thermal management, if we can run those algorithms at a system level or at a high level to do trade-offs, I think there's a lot of value.
But then the question remains, being a little bit provocative about it. We've seen system level annotation for virtual platforms for the last 15 years, literally. I mean, video was still video when it allowed you to annotate low power data into virtual platforms so that your software could be analyzed. The ability of annotating transaction level models with power information exists today. The challenge I see from a vendor perspective trying to help the users is that those system level methodologies itself actually are not well enough adopted to actually make it usable, really, because it's an adjunct to something which is not that fully adopted yet, and it's certainly with usability and the effort you put in there, right? Just the annotation to a transaction level model isn't really that complicated, but then deriving from the gate level where we got the A and getting it all the way back to the transaction level model, keeping that in sync.
Yeah.
That is really the difficult part, right? Because it involves all the implementation engines.
Yeah, it kind of goes to the model continuity across.
Exactly, your third
right,
challenge.
that's really the key thing. But the other point, Frank, is also, it's really the modeling formalisms itself, right? I mean, I can write a system level model with some Markov chains. I can write something else. I mean there's really, to some degree, right, behavioral RTL, we have some very strong formalisms in which you can actually write. But once you cross the RTL level, it can get very open-ended, right? It's purely algorithmic. I can write my anything else. But
I
there
would
maybe
actually find even, it's not even RTL, it's actually then also the level of hardware and software, right? So once you go beyond the hardware, in general, you have issues.
Right.
Yeah, I think it's the question is, how much does it cost to do that modeling versus how much you're willing to pay? And I mean, the cost is coming down and how much we're willing to pay is going up, so they'll converge at some point. But right now, a virtual platform is pretty heavy. I mean, just to get power numbers to set up a virtual platform, I know you can do it in certain ways, but...
Oh, but it's heavy, absolutely.
Yeah.
It takes a lot of effort.
So if there was a power-specific tool at the system level where we wouldn't have to pay that huge price, that would be good.
Right, and one of my pet peeves in all this is these tools at the higher level, even though I've been working in this for the last 20 years, if they're not becoming part of the essential path of implementation, they will be very hard to adopt and an additional effort to develop, right? That's why actually people are using more and more emulation and even FPGA, which is really the brute force answer. Instead of doing a model at a higher level of abstraction, you just do more power, no pun intended, right? You just apply more pressure, you do brute force acceleration on it to get more data and then deal with more data, right? And that gives you the breadth of a longer cycle in software, but it hasn't really used abstraction in it. So, and then you're willing to pay for it because the cost of modeling with all the effort in there, the time it takes, just brute forcing it with a bigger iron element, so to speak, is actually a alternative that then is considered. And the accuracy at the RTL model is at the RTE level is also bigger.
And we do get a lot of value out of emulation, and we've caught a lot of power bugs with emulation. But the problem that I'm trying to address, it's emulation addresses too late in the design flow. We want to do something, early on in the design flow to do exploration.
Right.
So oftentimes our emulation, when it's actually running mission mode software, we're beyond all the architectural decisions have been made.
You can't make any changes anymore at that level. Challenge though being, I fully agree with that, challenge though being that the level of accuracy you would require to actually make those decisions feasibly in the very front end is higher than what you normally get at that early architecture level, right?
But that's okay. I mean, we can have bigger error bars at the early, the decisions we're making, we can tolerate bigger error bars early on.
Right, yeah. But it's certainly a challenge, yeah.
Okay, that was a good provocative question. Are there any more questions from the audience? Well, I think with the discussion that we just had, I think that's a good time, a good point to wrap this up. I want to thank our audience for attending. I especially want to thank our panelists who not only spent the time in preparing, but also in engaging in a very thoughtful and detailed dialogue. Thank you all. Let's give them a hand.